Hey folks, my name's Nathan Johnston, and today we're going to talk about rates of change of a function. In particular, we're going to look at two different types of rates of change. We're going to look at the average rate of change of a function over an interval, and also we're going to talk about the instantaneous rate of change of a function at a point. Okay, so the first of these, the average rate of change of a function, it describes how quickly that function is changing over some interval, okay, from one point to another point, okay? And you may have already seen something like this before. And it's the easier of the two rates of change to deal with because it has a very nice formula, right? The way that you compute the average rate of change over some interval, it's just you compute rise over run, right? Okay, so the top here, this is just how much the y value changes from x1 over to x2. It's the difference in the y value. So that's the rise over that interval. Okay, and then the run, it's just, well, how much did x change from x1 over to x2? So it's x2 minus x1. That's your difference in x values. And that's all this notation on the left here means. This delta, this sort of triangle looking symbol, that's delta, and it stands for change. So this is change in f, or change in your y value, divided by change in x, okay? So overall, you just get rise over run, which is like your slope. It's your average rate of change over that interval. Okay, so let's draw a picture here. If your function is y equals x squared, right, imagine that this represents, position of a car X seconds after it started taking off. Okay, so like if after 1 second, it's up here at a distance of meter, or pick units so that the speeds actually make sense here. After 2 seconds, it's up here at 4 meters along the road. After 3 seconds, it's at 9 meters along the road. Okay, it's the world's slowest car, but whatever. After 4 seconds, it's up here at 16 meters along the road. And you want to know, well, how quickly was it moving over some time period, right? Say between 1 second and 3 seconds. How quickly was that car moving? Okay, so what you do is you compute the average rate of change from 1 second to 3 seconds, you compute the slope of this line segment here, okay? This slope that, it intersects the function, when x equals 1 and also when x equals 3. Okay, and the slope of that line segment really it's just this function here, okay? So the slope of that line segment is the average rate of change, okay? And so, let's just plug in all of our pieces. The left point here, that's x1, and so the corresponding y coordinate, that's f of x1, okay? And similarly, our right x point, that's x2, and the corresponding y value is f of x2. Okay, so now let's compute what that average rate of change is, what that slope is. Okay, and in this particular case, we chose our left endpoint x1 to be 1 and our right endpoint x2 to be 3. So now we're just going to plug those in. Okay, x2 is 3, x1 is 1. Similarly down here, x2 minus x1. Okay, and now we just compute what f of those numbers is, right? Our function here is just the squaring function. F is, x squared. F of x is x squared. So f of 3 is 3 squared, which is just 9. And f of 1 is 1 squared, which is just 1. And now it's just 9 minus 1 over 3 minus 1. That's 8 over 2. It's just 4. Okay, so the slope of this line segment here is 4. The average rate of change is 4. So over this time period between 1 second and 3 seconds, on average, the car was moving at 4 meters per second. Okay, so just as a brief note on terminology before we go on from here and do other things, if we extend the line segment that we drew to an entire line, okay, then what we get is something called the secant line, okay? And actually there are lots of different secant lines, right? Because it depends on which 2 points on the curve you pick. But if you pick 2 points on the graph of a function and then draw the line that goes through those 2 points, that's called a secant line of the function. In this particular case, it's the secant line going through 1, 1, and 3, 9. One of the undesirable properties of the average rate of change is that it discards a lot of information about the function. It only cares about what happens at the endpoints of the interval that you're computing the average rate of change over. Okay, so for example, if you have a function like this, well, this type of function, it might represent, for example, the number of millions of people infected by a virus in a pandemic over years. Okay, so in our x-axis, that's number of years since the pandemic started, and y-axis is number of millions of people infected at any given time, for example. Then sort of what happens is typically near the pandemic, it's going to peak, and then, maybe a vaccine happens, and then it starts tapering off, and eventually, hopefully, it gets back down to 0 people infected. Okay, but if you have a function like this and you do something silly like compute the average rate of change over 4 years, say from 0 to 4 years, then what's the average rate of change? Well, the average rate of change is just 0, right? It's rise over run. And what's the rise from x equals 0 to x equals 4? Well, it's just 0 minus 0. Okay, there is no rise. It went up, but then it came right back down. Okay, so over the entire interval, the average rate of change is just 0. You went from 0 people infected to 0 people infected. Okay, so for functions like this, the average rate of change, it's very, very bad. Okay, so now we say in our best infomercial voice, there's gotta be a better way. And, now I'm going to sell you my product. I'm going to sell you that better way. The better way is the instantaneous rate of change. Okay, what the instantaneous rate of change does is it measures the rate of change of a function just at a single point, not between 2 points, but just at a single point. It measures how quickly the function changes at a point. Okay, so how do we compute this? Well, that's what we're going to start talking about now, because it's not as simple as it was for the average rate of change. It's not just rise over run anymore, because, we're only talking about at one point. Okay, so just bringing back the same graph that we had up a couple slides ago, just to remind ourselves of it, and now I'm going to start tweaking it. I'm going to think about, well, how can I change this to compute the instantaneous rate of change rather than the average rate of change? Okay, what I'm going to do is I'm going to start building a table here, okay? And how I'm going to build it is I'm going to change this interval that I compute the average rate of change over. Okay, I started off computing it over the interval from 1 to 3, and I got an average rate of change of 4. Okay, so I computed that a few slides ago. In other words, the slope of this line is 4. What if I shrink down that interval though? What if I bring that right endpoint 3 over to the left towards the left endpoint 1? Well, now I'm going to get another average rate of change, but it's going to be over an interval that's a little bit closer to that point at 1. Okay, my goal here is to compute the instantaneous rate of change just at 1 itself, at this point 1, 1. What's the instantaneous rate of change there? What's the slope there? Okay, so if I shrink this interval down a little bit so that now the interval is just from 1 to 2, so I plug in these 2 points, 1, 1, and 2 f of 2, which is just 2 squared or 4, so this is the point 2, 4, then I go through my average rate of change calculation. I'm going to find that the average rate of change this time is 3, just using that same formula that we used a few slides ago. Okay, if I shrink the interval down even more, so now it's the interval from 1 to 1.5, again, that just means I'm plugging in a right endpoint that's a little bit closer to the left endpoint now. I'm going to find that the average rate of change at this time is 2.5. Now, this line, its slope is decreased down to just 2.5 now. If I go a little bit farther, now the interval is just from 1 to 1.1. Now the average rate of change is just 2.1. This line, again, it's got a little bit shallower. Now its slope is just 2.1. If I shrink down even more, so that my interval is just from 1 to 1.01 now, very, very tiny interval. Now the average rate of change is 2.01. That's the slope of this line over here. And maybe now you can sort of see what's going on here. As the interval gets smaller and smaller and smaller and smaller, the average rate of change over that interval is getting closer and closer and closer to 2. Okay, and that actually does happen. We're going to show that in a second. Okay, so this line here, what we get sort of as the interval gets smaller and smaller and smaller and smaller, this line, we call it the tangent line. Okay, so if you have a line going between 2 points on the graph of a function, that's a secant line. But if it's a line going through just 1 point on the graph of a function and that line has the same slope as the function, okay, then it's a tangent line. And that second point is really important. It has to have the same slope as the function. In other words, it just comes in and barely touches the graph of the function and then goes away, right? If I do something like this, a line here, yeah, that goes through 1 point on the graph of the function, but it's not a tangent line because the slope's wrong. Okay, the key feature is it goes through that point and it barely just comes in and touches the graph of the function and then goes away. That's what makes it a tangent line. Okay, and this tangent line, it's going to have slope equal to 2. Okay, it's going to have slope that's equal to sort of this limit of average rates of change. Okay, and really what's going on in this table, I mean, it is a limit. We're computing what happens as this right endpoint approaches the left endpoint. Okay, so that's what our formula is going to be. That's how we're going to compute instantaneous rates of change. Okay, the instantaneous rate of change, we change notation slightly from the average rate of change. Remember, the average rate of change, we had delta f over delta x. Well, to signify that we're talking about an instantaneous rate of change, we instead use this notation, df over dx. Okay, and the d sort of signifies that it's a rate of change still, just like the deltas, but it's instantaneous. Okay, so that part's just notation. And then the rest of it is, well, this was just the formula for average rate of change. And all we've done is we stuck a limit in front of it, okay? And what limit is it? It's the limit as the right endpoint, x2, goes over to the left endpoint, x1. Okay, and as you take that right endpoint over to the left endpoint, in other words, as you make the interval smaller and smaller and smaller, well, you're going to get the instantaneous rate of change. Okay, and just for the sake of simplifying notation a little bit and making this a bit easier to work with in practice, we're just going to change notation slightly. Instead of having x1 and x2 in this limit, I'm going to change the notation so that x2 is just x, okay? So if I go back up, this was the formula that I originally wrote, and notice where the x2s and x1s are, okay? So I've got an x2 in each of these slots and at the first slot, and everything else is an x1. Well, now I'm just going to change notation so that all those x2s become x's. Okay, so that's all I've done. And the reason for that is just that I'm going to think about the x2, which now I'm calling x, I'm thinking about that as the variable in the limit, right? It's the thing that's changing in the limit, whereas x1 is fixed, okay? And usually in math, you know, we give like the variable name to the thing that's changing, and then we use subscripts for things that are fixed, okay? So I'm leaving x1 fixed, but x, which used to be x2, that's allowed to change. So it's just a change in notation. I'm not actually changing the math or anything here. Okay, but now if we want to convince ourselves that these things all make sense and what we've done is right, let's go back to this example, f of x equals x squared, and let's actually compute this limit. Let's compute this instantaneous rate of change. Okay, so I start just by plugging in x1. I look on my graph and, oh, x1 is 1, right? That's the fixed point that I'm plugging into my function. So that's all I've done here. I've replaced all the x1s by 1s. Okay, and then next up is, well, now I'm going to plug in what my function is. F of x equals x squared, so f of x becomes x squared, and minus f of 1, so that's minus 1 squared, so it's just a minus 1, okay? And now, what do I have? Now I have a limit of a rational function, right? This is a rational function. It's a polynomial over a polynomial, and we learned how to solve limits of this type in the previous lecture, right? So what I'm going to do is I'm going to just factor the top and bottom. Fortunately, the bottom, the denominator, x minus 1, is already factored, right? The denominator is just linear, not much I have to do there. The numerator, though, is quadratic, x squared minus 1, so you can factor that however you like. In particular, this one, it's just a difference of squares, right? X squared minus 1 squared, so that factors in this way, okay? And the really nice thing here is, well, notice what happens. X minus 1, cancel, cancel, with the x minus 1 on top and bottom. Okay, so all we're left with after we do that, we're just left with x plus 1. And now this is a continuous function. We can plug x equals 1 into it, and all we're going to get is just 1 plus 1 equals 2. And that's exactly what we saw earlier, right? That was our guess for what the instantaneous rate of change would be based on our table of values. And now we see that, yeah, it actually is 2. If you take intervals that get smaller and smaller and smaller, the average rate of change is going to go towards 2. So that's what the instantaneous rate of change is. That's what the slope of this tangent line is. Okay, so this instantaneous rate of change, this value of 2, that's something that we call the derivative of this function. It's the derivative of the function at x equals 1. And all that means is instantaneous rate of change, or slope of the graph of the function at that point. Okay, and basically the rest of this course is going to be about derivatives and all the amazing things that you can do with derivatives. So we'll start talking about this instantaneous rate of change, this derivative, a little bit more formally next lecture. So I will see you then.